Okay, so welcome to class 20. So, we will continue our discussion on again looking at just the underlying point groups in a material and then trying to understand the properties of the material, right. So that is what is leading us to what is called structure or symmetry property correlation, right. So, today we will do it sort of qualitatively, but so once I give you a brief introduction of what space groups are, we will do this more quantitatively, right. We will actually look at couple of properties, look at how symmetry will tell you what tensorally elements exist, what does not exist, and so on. If you so we have done this in the past for a third rank tensor and with one operation, which is the centrosymmetric which is the inversion operation, and we said third rank tensors or first rank tensors or fifth rank tensors, if you have inversion they become 0, all the elements become 0, right. So we will do similar sort of structure property correlations for other symmetry operations, other symmetry groups, right. So in the upcoming classes, but to continue our discussion on what point groups are, we ended last class by asking the question how many of these point groups are non-centrosymmetric, and we had answered that 21 of them are non-centrosymmetric and 11 of them are centrosymmetric, right. So, if I am looking at a third rank tensor like dijk, just give me 1 second. Yes. So, if I am looking at a third rank tensor such as dijk, I am not going to consider the 11 centrosymmetric point groups. Why? Because symmetry, in this case centrosymmetry, forbids piezoelectricity. This is a very strong statement, right. So, symmetry can forbid things and there is nothing you can do about it, right. You have to reduce the symmetry, that is it. If you want to make a material piezoelectric and so the material crystallizes in such a symmetry, such a point group symmetry that there is inversion symmetry, right, you have to break it somehow, right. Your materials engineering strategy should be such that you break this inversion symmetry. I will strain the material, I will apply some field, I will do something to break the inversion symmetry, right. Or I will change the composition, right. So the standard trades of the game, right, to make it non-centrosymmetric. Only if you make it non-centrosymmetric can I measure some sort of a piezoelectric coefficient. Okay. So symmetry, centrosymmetry for example forbids piezoelectricity or forbids a second harmonic response from these materials. Okay. And we also said that there is another accidental point group which is the 432, where also third rank tensors dijk go to 0, right. So in general, if I am searching for piezoelectric crystals, I look at 20 point groups, right. So 21 minus the 432, right. So 432 is not good enough. So all the piezoelectric tensors are going to be 0 even in 432. Okay. So not because it has inversion symmetry, it does not have inversion symmetry, but just these operations make the tensor 0. Okay. That also we will prove at some point. Okay. So then we go to what are called polar groups, right. So we can further classify these materials as polar groups, the point groups as polar groups and non-polar groups. Okay. So typically so every point group, so we call something a point group because there is a unique point, right, about which you have some symmetry operations. For example, if I look at 4 bar, right. So, 4 bar I said I have 2 circles here, 2 dots here, right. So, this is my unique point, the so okay. So, the unique point I will color it differently. This is my unique point about which I have a 4 bar symmetry, right. It is not an axis, it is a point about which I have 4 bar symmetry, right. So, 4 bar is, there is a unique point of high symmetry. Okay. If I take 6 by m, right, even in 6 by m, right. So, 4 bar does not have inversion symmetry, but it has no inversion symmetry, remember that. But I have a unique point of high symmetry. Okay. 6 by m has inversion symmetry, right, or okay. So, let us just make it 2 by m, or yeah. So, 2 by m we said has inversion symmetry, there is a two-fold axis, right, and this is the mirror, right. So, if I have one here, the same thing goes there and then the same thing goes here, right. So, there is inversion symmetry, okay. But so this point where the mirror plane hits the two-fold axis of symmetry, there is a two-fold axis of symmetry being hit by the mirror plane, this is two-fold axis, this is the mirror plane, right. So, the point in 2 by m, or in general in n by m symmetry operations, the point where the mirror plane hits the two-fold axis is a unique point. Okay. So, you have a unique point about which there are so there is a so unique high symmetry point, right. Not all points are equal, right. So, this point where the mirror plane hits the two-fold axis of symmetry or n-fold axis of symmetry is unique, right. So, that is a unique point of high symmetry. Okay. However, you have certain point groups, we still call them point groups, such as just 2 or 6 or 4 or 3, right. So, these are simple rotations, but in the form of a group. So, a 2 will include a one-fold rotation and a two-fold rotation, right. So it is a group, okay, where so okay, 2 means I have two-fold axis of symmetry, right, where so I have a two-fold axis of symmetry, I am going to have a asymmetric unit here, and I am just going to rotate it by 180 degrees and have another asymmetric unit here. Just rotating I have to so this is not the entire axis here, the entire two-fold axis, right, if I am not cutting it with a mirror or anything else, has a set of points of equal symmetry. Every point is equivalent, right. So, every point is symmetry wise equivalent. I have a two-fold axis of symmetry about so set of points of equivalent, not set of points, has infinite set of points of equivalent symmetry. Right. So, I can go about any point on this two-fold axis or n-fold axis of rotation, and so about every point I have so I can rotate my asymmetric unit about that point, right. So, by 2 pi by n, and then I get the same this thing, right. So, so no point is unique along this axis, but the entire there is a line that is unique, right. So, or the axis is unique. So, I have a polar axis, this sort of an axis is called polar axis, right. So, in my crystal, meaning no point along the axis is a unique point. Is a unique high symmetry point. Or in other words, all points along the axis have equally high symmetry. Okay. So, I mean you could argue that okay, this is not really a point group because I am not talking about one point, rather I am talking about set of points, but this actually is a point group indeed, right. So, group theory does not forbid it from being called a point group, right. So, this is a point group, but I do not have a unique point, I have a set of points along the line, an infinite set of points along the line which are so there is no special high symmetry points along this line. Okay. So, such point groups where I cannot find a unique point about which I have I have a unique high symmetry point are called polar groups, right. So, point groups I will which do not possess a unique high symmetry point are called polar groups. Okay. So, for example, all these rotations, right. So, two-fold, one-fold also, right. So, that is an identity operation, two-fold, four-fold, six-fold, three-fold, right. All these are polar groups as point groups, right. So, if I have two-fold, I just have one two-fold axis of rotation, the other one is a trivial one-fold axis of symmetry, right. If I have three-fold, I have only one three-fold axis of symmetry. Okay. So, these are all polar point groups. Okay. So, polar nature and then you can actually list out all the polar point groups. So, all the polar point groups here are shown with an asterisk, right. So, here so let me change the color and probably I will make it this color. So, the 1 of course, right. So, 1 is a polar point group, 2 there is only one two-fold axis of symmetry, right. Mirror, if I have a mirror plane, right. So, any point along that plane is you are mirroring, right. So, you are doing x y z goes to minus x y minus z, there is no unique point about that plane, right. So, mirror is a polar operation is a polar group, right. Then you can add operations and then show that MM2 is a polar group, 4 is a polar group, 3 is a polar group, 6 is a polar group, all this we have seen, 3M is a polar group, right, 6mm is a polar group and so on and so forth. Now, or 4mm, right. So, now what is the use of looking at polar groups, right. Now, turns out that you can show this, I am not going to show this in this class. So, there are 10 polar groups altogether. Okay. Now, these polar groups, polar nature is a crystallographic idea. Which means if I say that my crystal is polar, right. So, it means there is a unique axis, but there are no unique points about this axis. The axis, all the points along this axis are equally symmetric, right. So, but I have a unique axis, right. Okay. Now, if I have a unique axis, so my crystals, so polar, that is it, that is what is meant by my crystal being polar, right. So, polar means I have a unique axis, that is it, it is a crystallographic idea, right. So, people tend to confuse it with what is called polarization. Polarization, however, is an electrostatic idea. Okay. So, what is polarization? So, I mean people say okay, I have polarization because my crystal is polar, right. The statement is true, but not to be confused. So polar group does not say anything about polarization. It's a consequence, you know. So it just becomes a consequence that I have polarization for you know, my crystal which is polar, right. So it has nothing to do with you know, so polar is an idea that comes from crystallography. Polarization is an idea that comes from electrostatics. So what is polarization? We looked at what polarization is. If I have a net dipole moment, right, you know, so in certain materials there is going to be a net dipole moment even when I do not apply any field, right. So we have done this, right. So we have said that you know, the displacement is actually equal to, so in vacuum, right. So if I have a dielectric in vacuum, so this is vacuum, sorry, if vacuum is my dielectric and these are my parallel plates, right, I apply an electric field E, okay. Then I create charges or charge density which is given as displacement charges, which is epsilon naught E. This is in vacuum, right. So I think we did this in one of the first classes. So I will just rush through this. But if I have a material, right, so I have charges which are given by vacuum charges, which is epsilon naught E, but the material itself will get polarized, right. So I have polarization charges also, which are put by the material getting polarized, right. So material, you know, so I have two parallel plates and there is a material in between, a dielectric material. The dielectric material gets polarized and put some positive charges here, negative charges here. So on the metal, if I am measuring the charge density on the metal, you know, to compensate for these positive charges to these negative charges, there will be some positive charges. These are free charges, these are bound charges. To compensate for these positive charges, there are going to be negative charges, again negative free charges on the metal. And by looking at displacements, you are looking at this charge density, the free charge density. Okay, that is the displacement vector. Okay, so a material additionally adds a polarization, right. This is, you know, now what is polarization really? So we said in you know, linear dielectrics, you polarize the dielectric by applying an electric field, right. So application of electric field polarizes the material, right. So without electric field I do not have any polarization. So by applying an electric field, which is the cause, I create a polarization which is the effect, and this is related by susceptibility times epsilon naught, right. So chi is the susceptibility. Okay, so this is the theory of linear dielectrics. You can also add E square, E cube and other things, but you know, so since we are saying this is a linear dielectric, we just stop at E. Okay, so we can Taylor expand it to E square, E cube, it does not need to be linear dielectric, right. So I have a susceptibility term which is a material property, right. So how much can a material polarize upon application of electric field times E. Okay. Now it turns out, you know, so here I am assuming that there is no polarization if E equal to 0, right. But it turns out in certain materials, however, by virtue of, you know, so by virtue of bonds in the material, bonding in the material, you can have what is called spontaneous polarization. I am going to call it as PR for a reason, R meaning remnant although I call it as spontaneous polarization. So, I would not use the word PS because PS has another connotation. So, let us use the notation PR, okay, for spontaneous polarization. So, spontaneous polarization means when electric field is 0, I still have charges on my metallic plate of the capacitor. And where are those charges coming from? Those charges are coming from because my material has a spontaneous polarization, right. So, now if I apply an electric field, if I write the total polarization is the spontaneous polarization plus chi epsilon naught E, right. So, this is the total polarization. Okay. So, there are, so the conclusion of this discussion is that there exist materials that have spontaneous polarization and there exist materials that do not have spontaneous polarization. Okay. You can actually show, right. So, here I am just going to give you a very basic simple example to show this, right. If, right, so then the statement that I am making here is if a material has spontaneous polarization, crystallographically that should be a polar material. Right, polar material, or it should belong to the underlying point group should be a polar point group. Okay. So, let us just take an example of something like 2 by m, right, and I am going to say that my material has a symmetry 2 by m, right. So, I have a mirror plane, I have a two-fold axis, right, and I am going to claim that I have a so this is the point group of the material. The question that I am asking for this point group is, can this sustain a spontaneous polarization? Geometrically asking, okay, so let us give a direction to spontaneous polarization, right. So, let the spontaneous polarization be in this direction, okay. But if I have some atoms that are giving me a spontaneous polarization in this direction, right. So, some sort of dipole moment which is created in this direction, the mirror plane would say that there should be another dipole moment in this direction, right. So, the net dipole moment should be 0. Okay. So, this symmetry cannot sustain spontaneous polarization. 2 by m cannot sustain spontaneous polarization. Okay. Now, you can also go for any material with inversion symmetry. So, here so there is inversion symmetry in this material. So, if I have an entity, right, which has a spontaneous polarization, this is going to be my entity, right, then I have to invert it about the center, and so this goes behind the plane, this is above the plane, right. So, this goes behind the plane with such a sort of thing, right. So, the net polarization equal to 0. So, materials with inversion symmetry also cannot support any spontaneous polarization. like that, you know, if there is a unique symmetry point in any material, you can actually go ahead and then, you know, so I am just giving you two brief examples. Even 2 by m has centrosymmetry, right. So this is a much general case of you know 2 by m, but you can keep on extending these arguments and actually show that materials that belonging to point groups that have unique high symmetry points, right. So, those materials cannot have spontaneous polarization. Okay. So, you can actually geometrically prove this. This is not a very hard statement to prove, although we are not going to do that here, right. We are just going to take that as a fact, right. So, so what can sustain spontaneous polarization? What point groups can sustain spontaneous polarization? Only those that do not have a unique point of high symmetry. Okay. So, that means that these are the polar groups, right. So, if I have spontaneous polarization in a material, that can only happen if my material already has a polar point group, right. But it is possibly, you know, so you can look at those materials that are polar but not have any spontaneous polarization, that is okay. So, symmetry is not you know, that is a coincidence, right. But if a material has some sort of spontaneous polarization, that means that that material should belong to a polar point group. So, that is the symmetry constraint. So, spontaneous polarization, which is an electrostatic idea, means that those materials should belong to polar point groups. Okay. Now, it turns out it is very rare to find examples of materials that do not have any polarization yet have a polar point group. So, there is a you know, so more or less every material that has a spontaneous polarization belongs to a polar point group. So, those materials are actually called polar materials. So, by definition, actually strict crystallographic definition, polar materials only have a polar axis, that is it, right, or a polar point group, right. However, it turns out that all these materials can actually sustain some spontaneous polarization, right. So, and the direction of spontaneous polarization okay, so direction of PR is actually you know either so if I have a polar axis, is polar axis either positive side of the polar axis or the negative side of polar axis. So, if I have a two-fold axis, it can either be pointing up the polarization or pointing down, right. So, these are all what are called polar materials, or you know, so you can also show that your property of pyroelectricity okay, I mean it is so let us come to pyroelectricity very soon, but you know, so you know, so the other statement which is quite obvious is any centrosymmetric material, right. If I have centrosymmetry, I am already identifying a point, a unique point, right. So, if there is a unique point, it cannot be polar, right. So, or all polar materials are not centrosymmetric. Okay. So, these are equivalent statements. However, polar is much more than non-centrosymmetry, right. So, polar is just a subset of non-centrosymmetric materials. groups. Okay. So we have 10 polar point groups among the 21 non-centrosymmetric point groups. Okay. All right. Now, I can look at any first rank tensor, and we said property tensor, and we said the first rank property tensor we know of is pyroelectric coefficient pi I, right. So, so you can actually show that the first rank property tensor pi I is 0 for centrosymmetric crystals, that we know, that is trivial to show, we also showed it, right. But pi I is also 0 for all non-polar crystals. If I have a unique axis, this is like saying if I have a unique point, not axis, if I have a unique point, I cannot sustain pyroelectricity, right. So, pyroelectricity only exists, right. So, pyroelectricity is if you remember, right. So, if I change the temperature, I am generating some polarization, right. This is pyroelectricity, right. So, just by changing the temperature, I am generating polarization in the crystal, right. Now, if my crystal is non-polar, I do not have the pi equal to 0. Okay. So, only in polar crystals by changing temperature can I generate can I generate any charges, right. So, that is what symmetry imposes, right. So, if I have non-polar structures, I cannot have pyroelectricity. Okay. So, as a result, because so pyroelectricity is a very good property that follows polar crystals, right. So, polar crystals are also known as pyroelectric crystals. Okay. So, if I have a unique polar axis, right. So, the crystal is polar, but polar crystals are also pyroelectric crystals, because pyroelectricity just if my crystal is polar, I have a pyroelectric property. If my crystal is non-polar, the pyroelectric property pi goes to 0. Okay. So, it is a one-to-one correspondence. Okay. Now, so in fact, if we go back to this presentation here, you show that these 20 non-centrosymmetric point groups, right, you can find piezoelectricity in them. Among them, right, you have 10 point groups with unique polar axis, right, which means you can find PS, right. So, if there is spontaneous polarization, that can only be found in these 10 point groups with unique polarization axis, and also you can find pyroelectricity, right. So, that is the pi. Okay. So, these are actually polar materials or pyroelectric materials, right. So, you will have pyroelectric materials. If I say that this material is pyroelectric, the only thing I ask for is, do I have a polar so if I am asked the question, will this material generate charges when I heat it, right, charges on the plate, that probably I can use for some sort of energy harvesting, right. Just by heating I am generating charges. So, I can use it as a battery, right. So, I can think of these energy harvesting applications. So, will this crystal do that? Then I ask a pertinent material symmetry question, does it have a polar point group, an underlying point group which is polar in nature, right. If it is polar, yes, you test it for your pyroelectric property, well, it may be good, it may be bad, that symmetry is not going to say, right. So, the pi can be either small or large. If it is large, you use it, if it is small, you do not use it, right. But so is the material capable of showing any pyroelectric property? Your symmetry will say, right. So, if it is polar, there is pyroelectricity, right. It can be close to 0, pi can be very close to 0, pi can be super small, but that symmetry does not care about that, right. So, it just says it exists. Now, go and measure. It is like a mathematician, right, the proof exists, now go prove it, right. So, that is what symmetry says. Symmetry says whether the property exists or does not exist, right. So, whether pi exists or does not exist. If I have a polar point group, pi exists. Okay. If I have a non-polar point group, I do not even need to worry about using that material for energy harvesting, pyroelectric energy harvesting. Okay. Now, The subset of that is what are called ferroelectric materials, but so we will actually spend some time on understanding what ferroelectrics are. But so today before we wrap up this class, I will just give you a definition of what well, okay. So, I will tell you what is the problem in defining a ferroelectric material. Now, so pyroelectric materials come from crystallography, right. So, if material is pyroelectric, let us change the color. If a material is pyroelectric, then I can say that this material is polar, right, polar crystal, or in other words all polar crystals are pyroelectrics, right. So, you will always have the pyroelectric property. Okay. Okay. So, that is a property that has come out of the symmetry, right. So, you can put in, you can prove to yourself that all non-polar crystals have pi equal to 0, right. So, this is a double implication. Now, what is a ferroelectric material? Now, ferroelectric material is that material that has a spontaneous polarization, PR exists, right, and this PR, so there is first constraint is there should be a spontaneous polarization, which actually means that the only materials that can be ferroelectric, right, are those materials. I mean, so from a symmetry or crystallography point of view, these are only so the database of materials where you search for ferroelectric materials are only polar materials or materials with polar point groups, right. So, there should be a spontaneous polarization, and we said if there is spontaneous polarization, that spontaneous polarization only exists in the polar materials, right. So, from symmetry arguments, a ferroelectric should be polar, okay, but that is not enough. You need a spontaneous polarization. First of all, the material should have polar point group, there should be spontaneous polarization, okay, which means without the application of electric field I should have some net dipole moment. We will look at examples of how that comes up in the next class. But so without application of electric field there should be a net dipole moment, okay. So, some spontaneous dipole moment, but this spontaneous dipole moment, the spontaneous polarization PR should switch upon application of electric field. Now, this is nothing to do with crystal symmetry anymore, right. So, now I am using some other switching property which is electrostatic in nature. There is a polarization up just like a magnet, right. So, upon application of electric field. So, I take this, I apply an electric field, I should make this a down switched polarization, right. So, and then I apply minus E and then it should come back, right. So, that is a ferroelectric material. It is not enough to have spontaneous polarization, right. You have many materials in fact, right. So, something like gallium nitride, aluminum nitride, right. So, so all these materials have a spontaneous polarization. Zinc oxide, right, the Woodside zinc oxide, right. We will look at all these crystal structures quite in detail, but all these materials have spontaneous polarization, but they are not ferroelectric, okay, because ferroelectricity just does not, the definition of it just does not come from crystallography. The definition is okay, one is it should have spontaneous polarization, but crystallography tells me whatever materials have spontaneous polarization should have a polar point group. That is where the crystallography comes in. It is a weak connection to crystallography, okay. Compared to pyroelectrics. Pyroelectrics are very strongly connected to the symmetry. If I have polar point group, then I have pyroelectric. If I do not have polar point group, I do not have pyroelectricity, right. here I should have polar point group, I will have ferroelectricity, but it is not guaranteed to have ferroelectricity if I have a polar point group. First I should have spontaneous polarization, and second, upon application of some electric field before I break down the material, because electric field can break down materials, right. So, if I apply huge electric fields, these electric fields can break down materials even before it switches, right. So, before it breaks down, the polarization should go from up to down. This is like a magnet, right. So, in a magnet I have a north pole, I have a south pole, right, so there is but if I apply strong enough magnetic field, I should be able to switch the north and south poles, right. So, so switching a magnet, right. So, it is very similar to switching a polarization, very similar to by magnetic field. Okay. So, these materials, the gallium nitrides, the aluminum nitrides, the zinc oxides, these are all very good polar materials, right. So, they have spontaneous polarization, they have polar point groups, underlying point groups, polar materials, but they are not ferroelectric because you cannot switch them before you break them, before you break down, before breakdown event happens. Okay. However, there are other materials such as, and we will spend some time in the next class trying to understand these materials, their underlying point groups and so on and so forth. Barium titanate, right, lead, this is BTO, right, lead, zirconium 0.48, titanium 0.52, or the other way around, I am always confused here. This is called PZT, right. So, you go to anyone working in piezoelectrics and then say PZT, they will just understand, right. So, it is a very standard material, right. So, PZT is a very standard material used in piezoelectrics and ferroelectric communities. Okay. So, barium titanate, PZT, then recently we have what are called doped hafnium dioxide, right. Then if I want to actually not look at oxides, I want to look at nitrides, aluminum scandium nitride, right. So, with certain proportion of aluminum and scandium, right. So, all these are materials that show a spontaneous polarization that can be switched. If you want to look at 2D materials, indium selenide. So, this is a 2D or a van der Waals material, right. So, you will see that in all these materials there is a polar group. Okay, fine, there is a spontaneous polarization, but the spontaneous polarization can switch upon the application of an electric field. Then I call these materials as ferroelectric materials. There are other things that they should satisfy, but so fundamentally these are the three primary constraints. Okay. So, to call something a ferroelectric material. Okay. So, we will do a brief detour to ferroelectricity in the next class. First, we will talk about some of these materials. How does it get its spontaneous polarization from an atomistic point of view, but then come back and then relate it to the symmetry, point group symmetry, okay. And then subsequently we will very briefly spend some time on what are space groups, how to identify the underlying point groups from space groups, and then end this module on symmetry and structure symmetry and move on to symmetry property correlations, okay. So yeah, I will see you again in the next class. Thank you very much.